At the Big Bang, there was just one unifying force, or so the research suggests. But as the universe began to expand and cool, four fundamental forces that still govern the universe today began to emerge. How these forces were unified in the beginning remains one of the great mysteries of physics. Our leading intellectuals, like Stephen Hawking, continue to wrestle with this problem. We talked about the Big Bang at length in the last lecture, but one aspect that we haven't discussed yet is what happened in those very first few moments. We know that the universe started with a dense, hot, tiny point, but somehow, within the span of 1/1,000,000,000 of a trillionth of a trillionth of a second, the universe entered a period of rapid expansion. We don't know how or what, if anything, happened to trigger it, but at about 10 to the minus 36 seconds after the start, a period of inflation began, with the universe expanding exponentially in tiny fractions of a second. In fact, some physicists refer to this inflationary period as the bang of the Big Bang, though again, the reference to an explosion is not quite accurate. Perhaps the most compelling argument is that at the start of the Big Bang, when the precursors of atoms and other particles were so hot and squished together that their boundaries were undefined, the forces, too, were unified in one pot of universal soup. But as the universe expanded and the ambient temperature cooled, the strongest of the four fundamental forces, which we simply call the strong force, separated from the others. Shortly thereafter, two more forces, which we call the electromagnetic and the weak forces, began to exert their unique powers. How the last force, gravity, came to be in those first few moments remains unknown. In this lecture, we're going to explore the four fundamental forces of nature that we think have guided the formation, expansion, and essence of the universe since that first trillionth of a trillionth of a trillionth of a second. Understanding what we've learned about these forces and their interactions is one of the keys to understanding our world and predicting how matter in the world will behave under different conditions. So, what do the four forces do? The aptly named strong force holds the nucleus of the atom together, and splitting the nucleus is what causes nuclear fission, the energy source that powers atomic bombs. The weak force is what's responsible for radioactivity, the force that governs the change of a neutron into a proton and an electron, which is then ejected from the nucleus during radioactive decay. What repels that electron from the nucleus is the electromagnetic force, which we met in the lectures on magnetism and electricity. As we saw, opposite charges attract and like charges repel. Charge describes the behavior of subatomic particles. Negatively charged particles like electrons are attracted to positively charged protons and repelled by other electrons. But we don't really know how a particle gets its charge in the first place. It's a fundamental property of the particle, but we can predict how it will behave, at least most of the time. Finally, there is the mysterious force of gravity, which we all think we understand intuitively. After all, gravity is why it's harder to walk upstairs than down them, and what keeps us from floating around in the atmosphere. But it's also arguably the most perplexing, because on a large scale, it's the strongest force. It's what's keeping our world orbiting the sun. But on a smaller scale, it is trumped by all of the other forces. How is that possible? Since all of the forces interact with one another and are often at work on the same object, it's helpful to start with the electromagnetic force, since that's likely the one with which we're most familiar. Electromagnetism is a fundamental part of atoms and their structure. It probably seems utterly banal nowadays that there are two possible electric charges, positive and negative, but if you think about it, there's an elegance to this simplicity that's also a little bit baffling. Why aren't there other types of electric charges? We can barely even imagine what these other charges could be, and yet there are different types of spin, for example, another fundamental property in subatomic particles. They can show half-integer spin, for example. It's not just clockwise and counterclockwise. So too, you could imagine that charged particles could have 2/3 of a charge or half a charge, but they don't. Instead, protons have a positive charge and electrons have an exactly symmetrical negative charge, such that the two cancel each other out entirely. In nature, in fact, the vast majority of atoms are neutral. They house an equal number of protons and electrons, though different parts of atoms might have slightly more or less charge, depending on exactly where the electrons are in their orbits. Just like light, then, electric charge is said to be quantized. It comes in indivisible magnitudes of charge, like photons of light. There's no such thing as half of a charge. But an ion or a molecule with extra charged particles can show a charge of, say, +3 or -2, depending on the imbalance between electrons and protons. So far, we've talked about electric charges, but the electromagnetic force incorporates both electric charges and magnetic fields. We covered both electricity and magnetism and their connection in earlier lectures, but to gain a deeper understanding of the electromagnetic force, let's consider how their relationship was first discovered. For a long time, electricity and magnetism were considered to be distinct forces, as astute observers discovered rocks that seemed to attract certain materials, and the effects of lightning and other natural forms of electricity. But in the 19th century, there was a surge in interest and excitement in the field of electrical science. This fruitful period of scientific discovery resulted, by the end of the 19th century, in the harnessing of electricity and the sweeping changes that bringing it into homes has caused. Many historians point to a serendipitous observation by the Danish physicist Hans Christian Ørsted one evening in April in 1820 as the first kernel of the idea that electricity and magnetism are somehow linked. He was preparing for a lecture, and as he was doing so, he noted that the needle on his compass was disturbed when he turned a battery nearby on and off. He postulated that magnetic fields, the areas surrounding a magnet that display magnetic properties, radiate from a wire carrying an electric current, but he couldn't figure out why. Then, in 1821, English scientist Michael Faraday discovered that magnetism could be used to generate electricity. He built a small motor that caused a wire to rotate around a magnet in the direction of the magnetic field if it had an electric current supplied by a battery. You can actually make one easily by yourself by attaching a small magnet to a battery, then adding a screw to one end of the battery and looping the wire from the tip of the screw to the top of the battery. The magnetic field will cause the wire to rotate around the battery. In his haste to publish the result, Faraday failed to acknowledge two of his colleagues, one of whom was his mentor, a slight that got him reassigned to other projects and left him out of the loop of electrical science for several years. But in 1839, Faraday demonstrated that only a single type of electricity exists, contrary to the popular views at the time. In fact, he proposed that electromagnetic forces extended from charged bodies and magnets and suggested that they follow lines of flux, invisible paths emanating from the objects like a fireworks display, a concept that was critical to the eventual invention of electromechanical devices. But he died before his idea was accepted by the scientific community. Scotsman James Clerk Maxwell picked up where Faraday left off and published a series of equations that show how electricity and magnetism are related in 1873. Specifically, he suggested that electricity and magnetism are, in fact, one force. He also underscored the implications of this notion all of which have been confirmed with ample evidence. Specifically, Maxwell suggested that the force with which electric charges attract or repel each other is inversely proportional to the square of the distance separating them. That is, the further apart they are, the weaker the force. The same is true for magnetic poles, and they too come in pairs with north and south, the equivalent of positive and negative charges in magnets, yoked to each other. The difference between poles and charges, as you know from our previous lectures, is that you can have a positive or negative charge in isolation. You can pick off an electron from an atom. But no matter how small you cut a magnet, it will always have both a north and a south pole. Finally, an electric current traveling down a wire creates a magnetic field around the wire, and the direction of the field, clockwise or counterclockwise, depends on the direction of the current. Up until now, we've talked about electromagnetism as it affects relatively large objects, but of course, electromagnetic forces also act on subatomic particles. For example, electrons orbit the nucleus of atoms because their negative charges are attracted to the positive charges of the protons. The Dutchman Hendrik Lorentz was the first to calculate the force acting on a charged particle in an electromagnetic field in 1892. Now we talk about the Lorentz force as the force on a point charge, a charge at a specific place in space resulting from an electromagnetic field. Understanding the Lorentz force and how electromagnetism governs particles helped scientists sort out the structure of the atom. And as they did so, they found that the electromagnetic force acts both on very short and relatively long distances, and that the range of the force is infinite, like gravity. But unlike gravity, there isn't a great difference between large and subatomic versions of the electromagnetic force. In fact, the electromagnetic force is so strong and far-reaching that it determines how chemical elements bond with each other and how different materials interact. The only reason that it doesn't seem to have a bigger influence on our world is because the charges cancel each other out. If it weren't for this property, it would far outweigh gravity in significance. But there was one mystery that understanding the electromagnetic force highlighted in terms of atomic structure. Namely, how does the nucleus hold itself together if it's made up of positively charged particles? Like repels like, after all. Well, this observation led to the discovery of the strong nuclear force, a force that we've harnessed to create and destroy in unfathomable proportions. The strong nuclear force is what holds the nucleus together, and the first person to model it was Japanese scientist Hideki Yukawa in 1935. He suggested that when protons and neutrons interact with each other, they exchange a particle called a meson, which transmits the force. It wasn't until the 1950s, when the first particle accelerators were built, that this particle was finally observed. Working with particle accelerators, physicists also found that the protons and neutrons were in fact made up of even smaller quarks. And the strong force then holds the quarks together, carried by gluons. Yes, they're called gluons, which then form the nucleus. Like electric charge, gluons also carry a charge, but there are 3 possibilities instead of just 2. That's why instead of calling them positive and negative, the charges that gluons can carry are called color charges, and each results in a different type of force. The strong nuclear force is 100 times stronger than the electromagnetic force at the subatomic level. It's the binding energy in the nucleus that is exploited using nuclear physics to create the intense reactions and energy release of nuclear power and the atomic bomb. While the strong nuclear force keeps the nucleus together, there is another force that governs the behavior of subatomic particles, and that's the weak nuclear force. As its name suggests, it's weaker than the strong force, and it's responsible for radioactive decay. The weak force changes quarks from one type into another by exchanging force-carrying particles called bosons, as was discovered in 1983. Over time, most quarks and a related set of particles called leptons eventually decay via the weak nuclear force. This decay is what makes radiocarbon dating possible. That leaves one more fundamental force, perhaps at once the most familiar and the most enigmatic of them all: gravity. Gravity, unlike electromagnetism, is not picky. It's the force that pulls together all physical bodies and is directly proportional to mass. So the more massive an object, the greater its gravitational pull. But contrary to our own personal experience, gravity is the weakest of the four forces at small scales. It feels to us as though it's quite strong, since it's keeping us attached to the ground, and defying gravity is hard to do. But when you compare its strength with the other force that we can see, electromagnetism, you get a sense for how weak it really is. If I drop a handful of paper clips, gravity will pull them towards the center of the Earth. And the Earth is huge, so its gravitational pull should be pretty strong compared to other objects. But all it takes is a little magnet to pull them in the opposite direction. One little magnet can resist the force of gravity coming from the entire planet. Okay, so gravity is weak, at least on objects as small as paper clips. But when you think about the fact that it's the gravitational pull between the Earth and the Sun that keeps this massive planet in orbit, you've got to admit that it's a pretty strong force too. And therein lies the enigma. When at least one of the two objects we're considering is small, gravity is weak. But when both objects are massive, like the Earth and the Sun, gravity is in fact the strongest force, overcoming all of the others. On Earth and elsewhere, we have a pretty good idea of how gravity affects medium-sized objects, larger than atoms, smaller than planets, like us. And this behavior is well characterized by Newton's laws, at least for objects traveling at low speeds, like you and me. Newton's law of universal gravitation breaks down gravity into the following two rules. Every mass-bearing particle attracts every other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In a nutshell, things with mass are attracted to each other with a force that increases as their masses increase, and the distance between them decreases. Bigger and closer means greater gravitational pull. But Newton's laws break down at both extremes, for very small things that travel fast and very large things like Mercury's orbit around the Sun. Mercury is the planet closest to the Sun, and its orbit is the most eccentric. At its closest, it's 29 million miles from the Sun, but at its furthest point, it's 43 million miles away from it. This eccentricity of its orbit puzzled astronomers for centuries and was especially bothersome to Newton, who knew that his laws of motion could not account for it. It wasn't until Einstein began thinking about the problem that a solution was finally proposed, 228 years after Newton published his law, in 1915. In his general theory of relativity, Einstein combined his ideas on special relativity with Newton's law of universal gravitation, and general relativity, as it's now called, is still the current description of gravitation in physics. What is special relativity then? In its simplest form, special relativity describes the fact that you can't really tell if you're moving unless you look at another object. That is, movement is relative. So if I stand very still and the camera doesn't move either, neither of us is moving in relation to each other. But both of us are moving in relation to the Sun as the Earth orbits around it. In addition to the idea that motion is relative, Einstein's theory of relativity had several other corollaries that are worth mentioning. It's now called the theory of relativity despite the fact that Einstein himself preferred the term invariance, because it demonstrates that concepts previously considered separable are in fact intrinsically linked, like space and time, and perhaps most famously, energy and mass. Arguably the most famous equation in all of science, let alone physics, is E equals mc squared, where E is the energy, m is mass, and c is the speed of light. Einstein's insight was that energy and mass are like convertible currencies. We can change one into the other. But the exchange rate is always fixed. It's the speed of light squared. Always. And because the speed of light is a big number, the energy generated by even a small increase in mass is very large. But another point that this equation makes is that nothing can travel faster than the speed of light. Why? Because the faster something moves, the more energy it has and the more massive it becomes. So particles traveling at 99% of the speed of light have more mass than the same particles traveling at 95% of the speed of light. This observation seems very weird. Pushing an object with little mass is easy. Pushing one with a lot of mass is hard. So accelerating a speedy particle gets harder and harder. It would require an infinite amount of energy to get even a tiny particle to reach the speed of light. And so light itself has no mass. But that's a topic for another time. So if relativity implies that movement is relative, and Newton's laws of universal gravitation tell us that the objects are attracted to each other in direct proportion to their masses and in inverse proportion to the distance between them, how does gravity act on large, moving bodies? Well, first we need to consider what it means to have a moving body and how gravity relates to movement. Einstein's theory of general relativity proposes that you can't tell the difference between the force of gravity acting on an object and the inertia of an object in motion. For example, have you ever been in an elevator with no outside cues and been unable to tell if it's moving yet? This usually happens when the motion is fairly slow. We're used to the force of an elevator moving upwards, making us feel as though we were being pushed down into the floor. But when that movement is slow enough, we can't tell if it's just gravity pulling our feet down to the bottom of the elevator or the movement of the elevator. What we feel is the change in the force. When an elevator moves upwards, we feel an increase in pull to resist that upward movement. But what if the elevator were stationary and the force of gravity was getting stronger? We wouldn't be able to tell the difference. So instead of thinking of gravity as a force, Einstein suggested that we think of it in terms of the curvature of space-time. Okay, this is where gravity gets a little wacky. Space-time is a notion in physics that puts both space and time on a single continuum so that we can talk about its shape as one thing. In this model, gravity creates curves in space-time by bending it in specific ways. The best way to imagine this phenomenon is to think of what would happen if you put a bowling ball on a trampoline. The trampoline surface would bend to accommodate the weight of the ball. Then, if you think of the ball as the sun and a marble as the earth, what would happen if you dropped the marble on the trampoline? It would be attracted to the ball and its motion would be affected by the curvature of space-time caused by the bowling ball. Now, if the marble is traveling very quickly, it can escape the depression caused by the ball, but its motion will still be very likely affected by it. In this way, Einstein conceptualized gravity not as a force per se, but as a distortion of space and time caused by the mass of an object. The larger the object, the greater the distortion. And when I say space and time are distorted, I mean that massive objects don't just pull things towards them, disrupting space. They also make time pass more slowly the closer you get to them. But speed matters, of course, and at speeds less than the speed of light and objects smaller than the most massive ones in our universe, time passes pretty consistently, and Newtonian laws of motion predict behavior just fine. Einstein's theories revolutionized our conception of the universe. But valuable as they've been, physicists are still working to reconcile them with what we know about how things behave at the subatomic level. Understanding the nuances of gravity might be interesting to physicists and astronomers, but what practical applications has this knowledge really given us? Well, one famous example of an application of Einstein's general theory of relativity, and almost certainly one that he didn't anticipate, is the invention of the GPS, or the Global Positioning System. It started out as an experiment in 1956 to test the theory by putting atomic clocks into orbit around a large object, the Earth in this case, to see whether time slows down as a result of gravitational pull. That is, does space-time really act as one continuum? And of course, Einstein's predictions were exactly right. A year later, in 1957, physicists at the Applied Physics Lab wanted to listen in on radio transmissions from Russia's first artificial satellite, Sputnik. As they listened, they soon realized that because of the Doppler effect, that's the change in frequency of a sound wave as it moves relative to the observer, they could also pinpoint the exact location of the satellite in orbit. Then, soon after, the Navy wanted to pinpoint the location of their submarines with precision, and they wondered if they could use the satellite to do the reverse, pinpoint the location at a specific point in time of the observer on the basis of where the satellite was located. This project was called Transit, or the Navy Navigation Satellite System, and was the first time that satellites were used to find objects on Earth, the precursor of our current global positioning system. So how does GPS work? Well, first, you need to have a series of satellites in orbit that can send and receive signals. Until recently, the Global Positioning System had 24 satellites in orbit that were used for this purpose. Second, you need a receiver on the ground that communicates with the satellites. These receivers, once only available to the military, are now ubiquitous. Many cars have them built in. Many different manufacturers sell different versions, and every smartphone is equipped with one. The receiver listens to the signals that the satellites are sending back to Earth. Each satellite sends a continuous barrage of messages via radio waves that include two pieces of information: the time that the transmission was sent and the satellite's position at that time. The receiver then uses the messages that it receives to calculate the distance to each satellite using the speed of light and the time it took to receive the message. Currently, the GPS system can determine the position of the receiver with an accuracy of 5 to 10 meters. And here's where general relativity comes into the picture. Remember that to provide accurate results, the precise atomic clocks on the satellites have to be corrected using Einstein's general relativity equations to account for the effects of the gravitational field. But why did we need 24 satellites instead of 1 or 2? Well, with one satellite, the receiver can determine its position within a circle that looks a bit like a spotlight that the satellite shines on the ground. With 2 satellites, 2 spotlights are created, and there are 2 places where they intersect, narrowing down the position to those 2 points. With 3 satellites, there is only 1 point where all 3 intersect, pinpointing the position of the receiver with even greater accuracy. Okay, so now we know why we would need 3, but why 24? Well, each satellite orbits the Earth twice a day. They're spaced such that they occupy 6 orbitals around the Earth, so that at any given time, there are at least 4 satellites that are in view from any place on Earth. 3 plus one more for good measure. In 2011, the Air Force actually added a few, so technically there are now 27 satellites in use at any one time. You might have noticed how much better GPS works now than even just a couple of years ago. Physics is not nearly done with its exploration of the four forces. In fact, arguably the holy grail of theoretical physics is the theory of everything that will incorporate all four forces, their interactions, and how they came to be. It's certainly on Stephen Hawking's mind. It does seem that every decade gets us closer. And just imagine the possibilities when we do finally understand what governs our universe. While we're waiting, we can now begin to explore just what the Big Bang and the forces of nature have created. At least, that part of the universe that we can observe directly, matter. Somehow, everything that we come into contact with, that we interact with, that we are made of, is a result of the Big Bang. As Fred Hoyle and Willie Fowler pointed out, we're all made of stardust. And in the next two lectures, we'll discover just how orderly and yet how bizarre stardust, or the elements of matter, can be. We'll travel from the very edges of the universe down to the nanoscopic world of the particles that make us who we are.